In this section, we're going to talk about the divergence and curl of vector fields. And before we jump in, I want to note that we are breaking with the order of the textbook. The previous section we covered was section 16.1 in the textbook, and now we're jumping all the way to section 16.5 in the textbook. We are going to cover the sections in between, but we're changing the order because those sections in between, they're going to be a lot easier to understand if we understand divergence and curl first. Okay, now divergence and curl, they are differential operators on vector fields. That's a fancy term, but it's something that we've dealt with before. We've dealt with differential operators on other kinds of functions. On single variable functions in Calculus 1, we learned how to take a derivative. That's kind of the fundamental differential operator. Earlier in this course, we learned how to take the gradient of multivariable functions. The gradient is another kind of differential operator. Divergence and curl are differential operators that apply to vector fields, and they're going to give us a lot of they're an important tool for understanding how to describe the behavior of vector fields. So let's start with divergence, and let's define what divergence is and how to find it. Okay, given a differentiable function f of xy, differentiable vector field and let's start with a vector field of two components. So our two components will be f of xy and g of xy. So at any point xy, this is the vector associated with that point. So given a differentiable vector field, the divergence of f is, and we put div in front. We have a couple different notations for divergence, but I'll start with this one. So div, short for divergence, the divergence of our vector field f. All we're going to do is we're going to take partial derivatives of the components of our vector field. So the partial derivative of, with respect to x, of the first component, and then I'll take the partial derivative of the second component with respect to the second variable, and I add them together. Okay? And in 2 dimensions, that's all it is. I take the partial derivative of the first component with respect to the first variable, the partial derivative of the second component with the second variable, and I add them together. Given a differentiable vector field in 3 components and 3 variables, then it's the same thing. I just have a third partial derivative with respect to that third variable. So in this case, the divergence of f is, so the divergence of f, if f is a 3-variable vector field with 3 components, we're going to do the exact same thing. We're going to take the partial derivative of the first component with respect to the first variable, the partial derivative of the second component with respect to the second variable, the partial derivative of the third component with respect to the third variable, and we add them all together. Okay? That's the divergence of a vector field in 2 dimensions and in 3 dimensions. Okay? Now you may be looking at this and thinking, this kind of looks familiar. This is very similar to a dot product. The structure is similar to a dot product, right? So I think about this, and we're maybe abusing the notation a little bit, but if I think of a vector of partial derivative operators like this, and then our vector field with components f and g, that's our vector field there. All I'm doing is I can think about this as the dot product of those two, right? This with that, that's that. And this with that, that's that. Okay? Same thing down here. I could think of this as a vector of partial derivative operators, and with the dot product of our vector field with components f, g, and h. Because I have first component with first component, second component with second component, third component with third component. Okay. Now this abuses the notation a little bit, right? Because this, I'm not really multiplying these two, right? So it's not really a dot product, not the way we defined it. But it looks an awful lot like a dot product, doesn't it? Okay. So this gives us another way to represent divergence. This this vector of operators here, we think of that as the gradient operator, that upside down triangle. Okay. And then our vector of functions, that's just our vector fields. Okay. So an alternative notation for divergence is the gradient operator dotted with the vector fields. Okay. That would be the same as the divergence of vector field f. And you will see both notations used. Okay. I am kind of partial to this second notation just because it helps me remember what we get, right? The formula for divergence. Note, though, that in any case, whether we're in 2 dimensions, whether we're in 3 dimensions, and no matter what notation we use, of course, the output of the divergence is a scalar. Okay, we get a scalar function when we take the divergence of a vector field. The divergence of a vector field is a scalar function. So let's take a look at a couple of quick examples. Here we want to find the divergence of a vector field, a 2-dimensional vector field. So I'm going to take the partial derivative of my first component with respect to my first variable x. I'm going to take the partial derivative of my second component with respect to my second variable y. Then once I take those partial derivatives, I'm going to add them together. Okay? So the partial derivative of the first component with respect to x, I get 2xy. Partial derivative of the second component with respect to y, I'll get cosine of x squared. And we're done. That's the answer. That's the divergence of this vector field at any point xy. If I want to find the divergence at a particular point, I'd plug in the particular x and y values of that point. Okay? Let's just do one more example. This one will be a 3-dimensional example. We want to find the divergence of a 3-dimensional vector field. So divergence of f, and I'll use the other notation for divergence just so you are exposed to both. And we want the partial derivative of the first component, xy squared z to the fourth, with respect to the first variable x. And just as a side note, just to remember that we're expressing our vector field here in terms of the standard unit vectors I, j, and k. So this, the expression multiplying the I vector, that's the first component of the vector field. The expression multiplying the j component is the second component of the vector field, and the expression multiplying the k vector is the third component of the vector field. All right, so just a different way to express the vector field. Okay, so partial derivative of the first component with respect to the first variable x. And then we take partial derivative of the second component with respect to the second variable y. That's 2x squared y plus z. And the partial derivative of the third component, which is y cubed z squared, with respect to the third variable z. And we're going to add them together. Our result should be a scalar function. We should not have a vector when we take the divergence. So the first derivative here, we just get y squared z to the fourth. The partial derivative of the second expression here with respect to y, we would get 2x squared. And the partial derivative with respect to the third component with respect to z, I'd get 2y cubed z. I don't have any like terms, so I can't combine anything, so that's as good as it gets. That is my answer. That is the divergence of this three-dimensional vector field. So we know how we define the divergence of a vector field. We know how to calculate the divergence of a vector field. But what does it actually tell us? What's it good for? Why do we care? So to answer this, let's kind of break down the divergence. Okay, so let's take an arbitrary two-dimensional function. The ideas that we develop here will also work for three-dimensional functions with a little bit of adjustment, but the extra dimension makes things a bit more complicated. So we're going to just focus on 2 dimensions. All right. Now, the divergence of vector field f, we're just going to take the partial derivative of function f with respect to x and the partial derivative of function g with respect to y and add them together. All right. So what I want to do is I want to go back and take a look at these partial derivatives using the limit definition of the derivative. And that's going to help us get some intuition on what this divergence is telling us. Okay. So partial derivative of f with respect to x, that's going to be the limit as h goes to 0 of f of x plus h minus f of x over h plus, hold on, it's a 2-variable function, right? Comma y minus f of x comma y over h. There we go. Got to include both those variables. Plus limit as h goes to 0 of g of xy plus h minus g of xy over h. Right? So here we're taking the partial derivative of f with respect to x because we're looking at how x changes. We let x change from h to x plus h, but we keep y fixed in both functions, right? It stays y through the numerator. And same thing for this. Partial derivative with respect to y because the y is changing, but the x is fixed. Okay? Now, I'm going to write these partial derivatives in a little bit different way that we haven't seen before, but it's going to be equivalent. And if you think about it for a moment, you may be able to convince yourself that it is equivalent. But it's going to make the understanding what's going on here just a little easier. Okay? So notice we're still taking the change in function f over the change in x, right? From here to here, I change my x from x minus h to x plus h. So that is a change of 2h. Same thing over here, all right? And as h goes to 0, this is going to get closer and closer to f of xy, right? So this is an equivalent way and sometimes useful way to characterize the derivative. As long as the derivative exists, this and this are equal as h goes to 0, right? Now what I want to do is I want to kind of use this and kind of discretize the divergence, right? So rather than looking at a little point, we're going to imagine h isn't quite 0, but is a little bit bigger than 0, and see what this is calculating for us, okay? So imagine this is our point xy, okay? This is where we want to calculate our divergence at, that point. Okay, and imagine we have some box around it, and we're really zoomed into our vector field, right? This box will exist in the context of some vector field. Okay, so some vector field, and we have a box that we've just placed within this vector field. Okay, the edge of this box is 2h, so from here to here is a distance h. Okay, which means this point here would be x plus h comma y, right? Because I'm going a distance of h. And this point here would be x minus h comma y. This point up here would be x comma y plus h. And this point here would be x comma y minus h. Okay. I'm just going a distance of h units away from my central point xy in each direction. Okay. So what each of these functions are doing is they're telling me how the vector field is changing at that point. Okay. So here I'm looking at f of x plus h comma y. And it's function f, so it's measuring the x component of the vector field, right? Function f is the x component of my vector field. So it tells me how that vector field changes left and right. And we're thinking about this as a positive value, so we're kind of measuring how much the vector field is moving in that direction. If f of x plus y is positive, then we're measuring that direction. If it's negative, it would be negative of this direction, right? It'd be the other direction, all right? Okay, and then we subtract f of x minus hy. That's this point. It's again measuring the x direction, but it's negative. And so it's checking how much the vector field is going in that direction. All right. So just to give you some sense of what's going on, if this is let me use a different color. If this is a vector on our vector field, then we could break it into two components. We are taking this component, okay? If this, do it right here, this is a vector in our vector field, we could break it into two components. And we're taking the negative of the horizontal component. We're counting it positive if we go this way, so we are counting it the other direction. Okay? And then over here, we have g of x comma y plus h. This is the point. G is the y component of our vector field, so it's measuring how much the vector field goes up and down. So at this point, we're measuring up and down, and it's a plus in front, so we count positive if we go up, okay? And down here, we have negative g of xy minus h. That's down here. Again, it's the y component of the vector field because of the g function. And it's a minus in front. So we're actually going to count it. If we go up, it counts as negative. If we go down, it counts as positive. So what I'm doing here is I'm drawing the direction which we would count the vector field positive in. Okay? That we would be adding positive numbers. So if all of these were positive, then which way would the vector field be going? Okay, kind of be going something like that. Okay, it'd be moving away from the point. I hope that makes sense. Okay, the divergence is calculating, it's adding up how much the vector field is going in each of these directions and then adding them together. And so if we take it as a total, if we get a positive number, that means the flow away from the point, the vectors moving away from the point are greater than any vectors going towards the point. So if we have a positive value here, the vectors are diverging away from the point. Okay? If we have a negative value, then we're going against these directions. Okay? So if we have a negative value, then on whole, the amount of vectors going in, the flow inwards towards the point is greater than the flow outwards away from the point. We are converging towards the point. And that's what the divergence tells us. Okay? If the divergence of f is greater than 0, then that means the vector field diverges, and let's specify a point, because at different points we could have different divergences, right? The vector field diverges away from the point x naught, y naught. Okay? If you think of the flow of some fluid, maybe the flow of air in space, the flow of air around you, if the divergence is greater than 0, that means the flow is flowing away from that point. Okay, would be losing density. Flow is away. If the divergence is negative, then it's not diverging, it's converging. Vector field converges toward the point on net. Doesn't mean nothing is flowing away from the point, but it means there's more flowing towards the point than flowing away from the point. Okay? And if the divergence at the point x naught, y naught is equal to 0, then that means we have a balance. The vector field is balanced. The flow outward and the flow inward are equal. Just to give you one quick application of this that I have experience with, if you're studying the flow of a fluid, say, let's keep it simple. You're modeling the flow of water. Okay. Now, in most practical applications, water is effectively incompressible. Very, very difficult to compress it. Basically, you cannot compress it at all. So if I push water over here, it immediately pushes back this way. Okay, you cannot compress it and you cannot pull it apart. All right, water is incompressible, which means if you're modeling the flow of water, you would want the divergence of water to be 0 because that means it's incompressible. You do not want the particles of water to diverge from a point because that means that we have less density at that point, right? And we've just uncompressed the water, which means the water gets compressed other places, right? And we don't want to squish the water in with a positive divergence, or I'm sorry, with a negative divergence, because that means we're squishing it in. We'd be compressing the water at that point. Okay, so for an incompressible fluid like water, one of the conditions is that the divergence of the flow of the water, the velocity of the water, has to be 0 at every point. Okay, this is a really important concept and applies in 2D as well as 3D. All right, the divergence tells you on net how much is flowing inward and how much is flowing outward from the point. Now that we have an intuition on what divergence is telling us, let's use it to think about the divergence for a few special vector fields. Okay, so let's take this first vector field and let's pick a point and say right here, just as an example point. I'm going to draw a box around it to help our intuition. Now, would we say the flow of this box, is there more flow inward or more flow outward? Okay, well, if we think about the flow inward, we do have some, right? We have, and remember that the vectors drawn are a small portion of the vectors there actually are. Every point has a vector. Okay, so, we have, kind of think about the vectors near the edge. So, there's some flow inward, certainly. Okay, there's some flow inward. But what about the flow outward? Notice the vectors over here. They're bigger, which means there's more flow. Okay, I have training as in fluid, so I always think of these vector fields in terms of flow. So if you think of it in terms of flow, these are flowing, but they're not flowing very fast. Small vectors, right? We have flow inward, a little bit of flow inward, but we have a lot of flow outward by comparison. Okay, the divergence of the vector field at this point is going to be positive. We have more flow out than in. Okay, now I do want to clarify one point. I've been drawing a lot of boxes. Really, divergence is divergence at a point. So we take that box and we take the limit. When we take the limit, we squeeze it down until we get to a point. Okay, so this is an approximation of the divergence. We discretize it. But really what we want to do is we want to take that box, okay, and shrink it down to a point in the limit until we get to the point. And that gives us our infinitesimal divergence. This box is just a rough approximation, but does a good job of giving us the intuition of what's going on here. Okay? So the divergence at that particular point is going to be a positive number because the flow is diverging away from the point on whole, right? There's some flow going in, but more is going out. Okay? We have a similar situation here, but in the opposite direction. Okay. Similar situation. We have flow going in, big vectors. Big vectors. So strong flow, fast flow going in. And then coming out, smaller vectors. Okay. So the flow going in towards the point is greater than the flow going outwards away from the point, which means the divergence of the vector field at this point is going to be negative. It's not diverging, it's converging. On whole, on net, there's more flow towards than away from. Okay? All right, one more example. This one's a little trickier. Okay? So looking at this point, we have some things flowing in. Okay? And then we have some things flowing out. And let me change the length on a few of these. Notice that the flow inward over here near the origin, near the origin. So these vectors here, they're small, right? I get a little flow in, I get a little flow out. Okay, but the further I move away from the origin, the faster the flow. So now I'm getting a little more flow in, but I have this kind of the same flow out, right? Over here, vectors are bigger, a lot of flow in, but kind of balance it, same amount of flow outwards. All right, this is an example where the flow in and the flow out balance. Notice there is a flow. Okay, it's not just static. If you imagine this being some fluid, it's not just like that the fluid's not doing anything. It's swirling, and it's swirling pretty good. But at any one point, the amount of flow of this fluid inwards towards the point is balanced by the flow outwards away from the point. This is an example where the divergence is going to be equal to 0. Okay? Next, let's talk about that other important differential operator on vector fields. That's the curl. So again, let's let f of xyz be a three-dimensional vector field. Let's make sure it's differentiable so we can actually take the derivative. Then the curl of the vector field is defined as, now the curl is a little more complicated to write than the divergence, but we have a way to help us remember. It'll probably look familiar. Okay, so the curl of f is equal to, we're going to take the determinant of a matrix where the first row is ijk. The second row is our vector of partial derivatives, partial x, partial y, partial z. And our third row is the components of the vector field, f, g, and h. Okay? And right away you could see that there's going to be another way to write this, and what does it remind us of? It's obviously analogous to the cross product, right? But instead of having a vector here, we have our partial derivatives, okay? So using that analogous operation of the cross product, we have an alternate notation. Instead of writing the word curl in front, sometimes we will use the gradient operator. Remember, this is we think of the gradient operator as the vector of partial derivative operators, and we take the cross product of that with our vector fields. Okay? Notice, because it's so related to the cross product, that the curl is only properly defined in 3 dimensions. Okay, now it's a really important operator. So later on, we're going to find how to extend it to 2 dimensions, but it's only properly defined in 3-dimensional space. And so let's take a look at an example of the curl in 3-dimensional space. Let's find the curl of this vector field. All right. So we know the trick to setting up the curl of this vector field, right? So the curl of f, to remember the complicated formula, we're going to take the determinant of the matrix, where the first row is ijk. The second row, and actually I'm going to give myself a little bit more room here to make sure I can fit the components of my vector field. The second row are my partial derivatives. So partial derivative operator with respect to x, partial derivative with respect to y, partial derivative operator with respect to z. And the last row are the actual components of my vector fields. So we have 3xyz squared, y squared sine z, y cubed z squared. Okay, and I'm going to take the determinant. So for this one, I'm going to have those two. Now, normally when we take the determinant, we multiply, right? That's not what we're doing here. We're using this as a way to help us remember the complicated formula for the curl of f. So we're not going to multiply. We actually take the partial derivative of this guy with respect to y. Okay. Now I'll break it into a couple of steps so we can see. But I'm going to put those two together, and then I put these two together. Okay. So these two together, I get partial derivative with respect to y of y cubed z squared minus, and now these two together, so that's partial derivative with respect to z of y squared sine z, and then multiply by the I. Right? So that'll be my first component of my of the curl of my vector field. Let's go for j, and I'll go to the next row just to make sure I don't run out of room here. So for j, oops, and because it's the j component, I'll put a minus in front, right? So this one and this one go together. So that's partial derivative with respect to x of y cubed z squared. Partial derivative with respect to x of y cubed z squared minus, and now these two together, partial derivative with respect to z of 3xy z squared. Partial derivative with respect to z of 3xy z squared. Don't forget the j at the end. And finally, the k component. Imagine canceling out the wrong column with the k in it. I'm going to put these two together and subtract what I get when I put these two together. Okay. So these two together, partial derivative with respect to x of y squared sine z. minus, put these two together, partial derivative with respect to y of 3xyz squared. And with the k at the end. All right. And I've already done it, but don't forget the plus, the minus, the plus. You alternate signs, right? All right. Now that I've broken down the formula, let's evaluate it. So our first component here, our I component, partial derivative of this with respect to y, I get 3y squared z squared. And partial derivative of this with respect to z, I'd get y squared cosine z. Minus y squared cosine z I. Minus, let's do this guy now, partial derivative with respect to x of y cubed z squared. There's no x in there, so that's just 0. Partial derivative with respect to z of 3xyz squared, that's going to be 6xyz. So minus 6xyz. J. Finally, let's work on this last row. Partial derivative with respect to x of y squared sine z. No x's in there, so that's just 0. Minus partial derivative with respect to y of 3xyz squared would be 3xz squared. So minus 3xz squared. And don't forget the k at the end. So our curl, all said and done, the first component in front of the I is 3y squared z squared minus y squared cosine z. The second component in front of the j is minus a negative 6xyz. That becomes plus 6xyz. And the third component is negative 3xz squared. So that is the curl of the three-dimensional vector field that we started with. Okay. Notice the output is a vector. That is different from the divergence. When we took the divergence, the result was a scalar function. When we take the curl, the result is a vector. Okay. Now this is the curl for any point x, y, z in space of the vector field. If I wanted the curl at a particular point, I would plug in the x, y, and z values for that particular point. So that's how you take the curl of a three-dimensional vector field. But as we'll soon see, the curl is a really useful tool for describing a vector field, just like the divergences. And we don't want to be limited to just three-dimensional vector fields. We want to be able to take the curl for two-dimensional vector fields. So if I have some two-dimensional vector field, okay, with components f of xy comma g of xy, how can I extend the idea of the curl in 3 dimensions to this two-dimensional vector field? So the way we do it is by embedding the two-dimensional vector field into 3 dimensions. So what we're going to do is we're going to embed it in 3D by taking the first two components, the same as the first two components of our original vector field f, and then just making our third component 0. So if we take the curl of this, it will give us an analog. It will allow us to extend the idea of the curl to 2 dimensions. Okay, so let's see what we get here. Let's just get the formula. So partial x, partial y, partial z, f, g, 0. So if I take the determinant here, and I'll go kind of quick for this first component, partial derivative of 0 with respect to y is 0. minus partial derivative of g with respect to z. Well, g is a function of x and y. There's no z's in there, so that'll also be 0. So my first component is 0. Okay? My second component, the j component, partial derivative of 0 with respect to x is 0. Partial derivative of f with respect to z. Again, f is a function of x and y. There's no z's in there, so if we're taking the partial derivative with respect to z, we're going to treat f of xy as constant. So in the derivative, it's 0 also. So the second component is also 0. And so we just have the third component here. We're going to have partial derivative of g with respect to x minus partial derivative of f with respect to y. Okay, notice this is going to be the case whenever we embed a two-dimensional vector space, two-dimensional vector field into a three-dimensional space. The first two components of the curl of that vector field are going to be 0. The only possibly non-zero component will be the third component. And so, because this is the only component that matters, whenever we do this, whenever we take the curl of a two-dimensional vector field, we just take this last component as the result. So we define this as the derivative of the second component with respect to x minus the partial derivative of the first component with respect to y. Notice the result. If we only take that one component, we take the result as a scalar. So when taking the curl of a two-dimensional vector field, we get a scalar, not a vector. When we take the curl of a three-dimensional vector field, that result is a vector. With the curl of a two-dimensional vector field, we only take the component that matters. That is a scalar. And so in this case, we call this the scalar curl. Let's see a quick example of this scalar curl. So here we have a two-dimensional vector field. So if we're going to take the curl of this, we're taking the scalar curl. So the scalar curl of this two-dimensional vector field, we're going to take the partial derivative of the second component with respect to the first variable. So partial derivative with respect to x of 2x cubed y squared minus the partial derivative of the first component with respect to the second variable. Partial derivative with respect to y of cosine x sine y. And so we get 6x squared y squared minus cosine x cosine y. That is the scalar curl of the two-dimensional vector field. So we know how to calculate the curl. We know how to do it in 3 dimensions. We know how to extend the idea to 2 dimensions and calculate the scalar curl. But why should we care? What is the curl telling us about a vector field? So let's try to get some intuition on this. We're going to approach it very similarly to how we approached the divergence. For simplicity, we will assume we're dealing with a two-dimensional function, a two-dimensional vector field. And then we'll talk in a little bit about how we extend some of these ideas to 3 dimensions. Okay? So the curl of f, we'd be getting the scalar curl, right? So we'd be getting the partial derivative of the second component with respect to the first variable minus the partial derivative of the first component with respect to the second variable. All right? Now, I want to break this down into our limit definition. So limit as h goes to 0 of, so partial derivative of g with respect to x, we'll let g change. or we'll let x change. We'll hold y fixed. So our numerator is the change in g over the change in x. And then partial derivative of f with respect to y. Here we hold x fixed, we let y change. Now, just as before when we were considering the divergence, it's going to be a little bit easier to think about this if I use that alternate form of the derivative. Okay. So we're going to approach this in the same way we did last time. We want to think about how this is acting about some point xy, and we want to think of what happens when h is close to 0, perhaps, but not 0. So I'm going to draw a rectangle around the point, right? And so we have 4 points here, x plus hy and x minus hy to the left and right. And xy plus h and xy minus h, top and bottom. And what we want to do is we want to find out what each part of this is measuring at these different points. Let's start with g of x plus hy. So that'll be this point here. And notice it's looking at the y component of the vector field. G is the y component of the vector field. Okay? And it's positive in front, so we're measuring the direction of the vector field at the point going this direction. Okay? That's the direction we're going to count as positive. We want to know how much of the vector field is going in that direction. And then this one over here, negative g of x minus hy. So x minus hy is there. It's again the y component, so we're measuring up and down. But because there's a negative in front, we're measuring the downward direction. We're measuring how much of the vector field at the point is moving in this direction. Okay? If it is moving in that direction, then we count it positively. It contributes to the total. If it's not moving in that direction, then we count it negatively. It counts against the total. Okay, so these two arrows are pointing in opposite directions. All right. Similarly, let's look at this guy, f of x comma y plus h. That's this point here. F is the x component of the vector field. That's this one here. So we're measuring how much the vector field is going left and right. And because there's a minus in front of it, we distribute that negative, it's minus. We're measuring the vector field going in the negative x direction. Measuring how much of the vector field is going in this direction, in the negative x direction. And similarly, f of xy minus h, we're measuring the vector field at this point. The f component, we're measuring the horizontal direction of the vector field, how much it's going left and right. And if we distribute in this negative right here, it becomes a positive. So we're counting the positive x direction as the positive direction. That's the direction we're measuring. We're measuring over in this direction. Okay? So if we put all these together, notice what's going on here. We're going around, right? So we're measuring in this direction. And if we go around, we measure going right to left, then top to bottom, then left to right. We're measuring how the fluid is swirling around the point, okay, or the vector field is swirling around the point. Draw that a little more neatly, a little better. Okay, that's what the curl tells us. The scalar curl, and as we'll see also the curl in 3 dimensions. It measures how the fluid swirls or curls around a point. Now again, this is a discretized version. We're looking at a big square. You need to imagine what happens as that square shrinks down in the limit and focuses on just the point. So it's the infinitesimal curling of the fluid around a point. The idea here is if you fixed a propeller or a fan in the vector field, okay, then the curl is telling you how the fan would turn. Okay, if the curl is positive, in this case the scalar curl, if the scalar curl is positive, it would turn this way. If the scalar curl is negative, and we're going against these arrows, then it would go this way. And if the scalar curl is 0, then there's no rotation. And in that case, we call it irrotational. Okay? In 3 dimensions, the situation is largely the same. The curl is telling us how the fluid is rotating around the point, or the vector field is rotating around the point. Okay, but in 3 dimensions, we just have more directions of rotation, right? In 2 dimensions, you could either rotate clockwise or counterclockwise. In 3 dimensions, there's just a lot more directions of rotation that we can have. Okay, so in 3 dimensions, remember the curl gives a vector, right? So maybe this is the curl of the vector field at a point. What that vector, the direction that vector is pointing in, is the direction orthogonal to the plane of rotation. Okay, so if this is the point, then the rotation, the net rotation around the point would be going here. Okay, orthogonal to the vector. The magnitude of the vector tells you the strength of the rotation. The larger the vector, the faster the rotation. Okay, and note that it follows the right-hand rule. If you curl your fingers around the direction of rotation, your thumb is pointing in the direction of the curl. Okay, the direction of the vector in 3 dimensions. Let's take a look at a couple of examples here. So I'm starting here with a 2-dimensional vector field. Let's see what the curl does right there. Okay, so you could see, for the illustration purposes here, it's a little propeller, and the curl is illustrated by the direction of the rotating propeller, right? The faster it is, the stronger the curl, and then the direction that it is rotating is the direction of curl. And if you look at it, it makes sense, right? The flow of the vector field, if you imagine this propeller in here with the center fixed, you could almost see it pushing it clockwise or counterclockwise, can't you? Now let's put it somewhere else. Let's put it maybe right here. Now look, it's moving even faster. Why? This one's a little harder to figure out, isn't it? But it's because the vectors on the lower right edge are really big. They're really strong. They're pushing it very strong. The vectors on the upper left are pushing in the same direction against the rotation, but because it's not as strong, the net rotation is still counterclockwise. Okay. Here, oh, it's, if you look closely, it's rotating, but very, very, very slowly. The net rotation is very small here. Okay, but if I move a little over here, now it's moving clockwise. It's rotating clockwise. The net force on this little propeller, the net curl, is greater on the right side than on the left side. It's pushing it more on the right side than it is on the left side, causing a clockwise rotation. Okay. Okay. So those are some, that's a two-dimensional example. Let's take a look at a three-dimensional example. All right. So this is a big mess. To be able to place the curl here, let's look at this from above. So this is the image from above. Let's place this curl somewhere, right? See if I could slow it down just a little bit. There, that's good. Okay. Now let's go back to 3D space and we'll see where that is. See where it is? Notice it's not just in a flat plane, right? Let me hide as best I can all those vectors. What's it doing? Okay. The curl, the vector there that you see, is orthogonal to the plane of rotation. The propeller there is rotating in the plane of rotation, in the direction of the curl. Notice it follows the right-hand rule. If your fingers move of your right hand, move in the direction of the rotation, then your finger is pointing in the direction of the vector you get, and that's the curl vector in 3 dimensions. Okay?